Complex numbers were invented to take roots of negative numbers. For example, I could ask, find the fourth root of minus 2. In general, I could ask for find the fourth root of some number a. Let's be precise about what we're asking here. We're really saying find all or find one solution to the polynomial equation z to the fourth equals a. This means exactly the same thing as finding fourth roots. If you have a number z whose fourth power is a, then z is a fourth root of a. Simple example. Solve z to the fourth equals 1. Well, when you were much younger, you would have learned about the roots plus or minus 1. Now that you know about complex numbers, we can add to that the roots plus or minus j. Fourth degree polynomial, we found 4 roots. Now we can ask a question, can we do this systematically? And the answer is yes. For that, we need a theorem, and the theorem is called the fundamental theorem. Fundamental, that means important, of algebra. We can state it very simply. A polynomial of degree n has exactly, no more and no less, n complex roots. So a quadratic has 2 roots, a cubic has 3 roots, a quartic has 4 roots, etc. In order for this to hold, we need to talk about repeated roots. I'll do an example. If I say to you, solve z squared minus 2z plus 1 equals 0, well, you'll have no problem factoring that into z minus 1 squared equals 0. And it might appear there's only one root, 1. But because there's 2 factors z minus 1, we say there are 2 roots and they're repeated. So the roots are both 1. 1 and 1. That's 2 roots. Often we'll say 1 is a root of multiplicity 2. So we'll use that term multiplicity for repeated roots. We'll illustrate using complex exponentials to find roots in 3 examples. So our first example is find the cube roots of j. Well, the answer goes like this. We write z cubed equals j, and now we want to write j in polar form. J has magnitude 1, so the factor out front of the exponential is 1. Then we have e, and it's got angle pi over 2. And that's been good enough so far, but now we need to remember you can add any multiple of 2 pi to the angle of a complex number. And so we'll add 2 pi n to that, where n equals 0, 1, 2, etc. In fact, it could be minus 1, minus 2, etc. Any multiple of 2 pi. In order to use this, we raise both sides to the 1/3. That gives us that z equals. When you raise an exponential to the 1/3, you just divide the exponent by 3, so that's j. Pi over 2 divided by 3 is pi over 6, plus 2 pi n over 3. Now something interesting happens. We're no longer adding multiples of 2 pi. We're adding multiples of 2 pi n over 3, and these are not all the same. Let's write out the first few terms. N equals 0, we get e to the j pi over 6. When n equals 1, that's 2 pi over 3 or 4 pi over 6. So we add that, we get e to the j 5 pi over 6. Next term is e to the j, we're adding 4 pi over 6, so we get 9 pi over 6. We'll do one more term. We get e to the j 13 pi over 6. This fourth term does repeat. 13 pi over 6 is 2 pi plus 1/6. So this right here is exactly the same as that. We don't need it. We have our three roots, 1, 2, 3. That's all the fundamental theorem tells us to expect. Now in the case where you have the angle pi over 6, we can write this out in a nicer form. Pi over 6 is the same as 30 degrees. We know about 30, 60, 90 triangles. So the cosine is root 3 over 2 plus 1/2 j. Then when we go to e to the j 5 pi over 6, we get minus root 3 over 2 plus 1/2 j. E to the j 9 pi over 6 is e to the j times 3/2 pi, which is exactly minus j. Let's finish by plotting these points in the complex plane. So I'll draw my plane here. As usual, I have my real axis and my imaginary axis. Now each of these roots has magnitude 1 because it's 1 times e to the j something. So I'm going to draw right here the unit circle of radius 1. Then I'm going to plot my three roots around the unit circle. E to the j pi over 6 is at an angle pi over 6. It looks about like that. I'll plot it right there on the unit circle. E to the j 5 pi over 6 is the same thing, but it's pi over 6 above the negative x-axis. And e to the j 3 pi over 2 or minus j, either way I can say it, I get a number down here. Notice that the angle between each of the roots is 2 pi over 3. That's not surprising. We kept adding multiples of 2 pi over 3 to our base angle of pi over 6.